here on the notes, you see one example. We want to design a combinational circuits with 3 inputs and 3 outputs. And when the input is smaller than 3, the output will be 1, otherwise 0. So that means you have 3 inputs, okay? So definitely you could give any type of the numbers with 3 bits, right? You could give 0 to 7 with 3 bits, right? We want to have one circuit like this. So let I turn off this and back to here. So we want to do this. We want to actually have one circuit. So which should has actually 3 inputs, and whenever this is and then 3, the output will be 1. Yeah, this is actually wrong. We need to correct that. We need actually 3 inputs, okay, and just 1 output, okay. So 1 output. So you should have 3 inputs, just 1 output. Whenever the input is smaller than 3, the output will be 1, otherwise 0. So you want to actually have 1 unit or circuits like this, 1, 2, 3 actually inputs. So I label that X, actually Y, Z, and 1 output. Okay, I call that F. So you have 3 inputs, you could actually make 8 different combination of 0, 1, right? For example, one example could be 0 and 0. So whenever I give the 0, 0, 0, so based on what I want to design, when the input is smaller than 3, 3, 0 is smaller than 3, the output should be 1, okay? So if that's 3 or greater than, the output should be 0. For example, if I give, I don't know, 1, 0, 1, which is, this is 1, this is 2, this is 4, which is 5. 5 is greater than 3, so then the F should be actually 0, okay? You want to actually design one circuit with the gates that you know, which do these things, that able to know your input is smaller than actually 3 or greater than 3. If that's smaller than 3, it's turn on the LED. So that means the output will be 1. If that's actually smaller than 3, the LED is off, means the input is smaller than 3, okay? So this is what we want to design. So similar with the other class, if you have any question, just please type that on our actually chat box. I could see the chat box, okay? So back to here. So this is what we want to do. So as we already know, we actually follow these first 4 steps that I mentioned in the beginning of this class, okay? So step number 1 is you should know how many inputs you should have for your circuit and how many outputs. So here we know it should be 3 input, then actually 1 output. So then step 2, you need to give a label, which I already did. My input is X, Y, Z, and the output is F. It could be any label, right? That's up to you. So for this case, I put X, Y, Z. If you don't like X, Y, Z, you could give A, B, C and give this just that's a label to represent input and output. Okay. So then you actually need to make a truth table. So you actually comes here and say, okay, I need a truth table. How many actually inputs I have for this circuit? It should be X, Y, Z. So I have X, Y, Z. These are the binary. So each of these variable could be 0 and 1. So I could have just 8 different cases. You just list that 8 different cases. So you say 1, 1, 1. Just extend this. So then let's do this 4. Okay. So then put actually 0, 0, 1, 1, 0, 0, 1, 1. So 0, 1, 0, 1, 0, 1, 0. Okay. So step number 3, you need to complete this actually truth table based off the function of your circuit. So I call the output F. So back to the definition of the problem, it says whenever the input is smaller than 3, the output should be 1, and whenever that's greater than 3, 3 or greater than 3 should be 0. So you tell me, whenever the first row, which is we have 3, 0, the F should be 1 or 0. Just type in that. Yeah, definitely should be 1. So because 0 is smaller than actually 3. So I put 1 here. How about this? How about next? Should be 1. Yeah, definitely right. That is smaller than 3. How about this, which is 2? That's right. How about this? Should be 0 or 1? Should be 0. Okay, so based on what we want to design, it's just say 3 inputs whenever the input is smaller than 3. So that means that 3 still should be 0, right? And the others, which is definitely greater than 3, should be 0. Okay, so you complete actually the truth table of your circuit. Okay, so then you actually know how you could make a circuit based off the truth table, right? You just comes here, say F equal to sigma midterm. You tell me which midterms. The F should be sigma which number of the midterms. It should be what should be midterm, should be include which midterms that we have here. Do we have 1 here or not? So we actually learned about this in before the midterm, right? You could write the standard form of the function with using the truth table. How you could actually write the standard form, that is sigma midterm. Just take the truth table. That should be the midterm that the function is 1 there, okay? So here it should be midterm 0, midterm actually 1, and the last one should be midterm 2. Definitely that's right, okay? So if even you could write with actually the other standard form, which is p max term and which max term, wherever the function is 0. So definitely should be 3 for all of these 5 cases that you see, 3, 4, 5, 6, and 7. Okay, you could write the standard form based off these 3 truth table. Okay. So now, what's the next step? You need to simplify this. That means if you directly implement with the gates, probably you actually end up with not simplest form. So that's the reason you need actually the K map. Okay. So here the function f, you tell me based off whatever you have here, the K map should be actually how many square we should have. So you just check this, you say, okay, 1, 2, 3. So this is a 3 variables, so 2 power 3, 8. So you actually need a K map with 8 square, right? So you actually make this. We already did this type of the works, right? So you put X actually here, y, z here. So put the 0, 1 for this, 0, 0, 0, 1, 1, 1, and 1, z. So just actually write the numbers for each of these squares. This is 0, this is actually 1, this is 3, this is 2. So this is 4, this is 5, this is 7, and this is 6. Okay, just double check that. 0, 1, 3, 2, 4, 5, 7, 6. Yeah, that's right. So now back to our table, so which is here, the standard form. It should be the midterm 0. I actually put the here 0, 1, and 2. Okay, so you tell me, do we have any set? Again, the same rule for the K map. You already know the number of the sets should be minimum, their numbers, their members should be the maximum. Then it's lead us to the simplest form of the function. So you tell me, do we have any sets with the 8 members? Yes, no? No, that's right. So how about the sets with actually 4 members? Do we have any? No, that's right. So then we go and looking for the sets with 2 members. How many sets with 2 members we have? Yeah, definitely 2. Okay. So where are there? So we could actually say, okay, this is should be the 1 sets with the 2 members, right? And I could take this with this and consider as another set with 2 members. So that means I have two sets with 2 members. So the simplest form of the f equal to, so write the corresponding terms for these terms. So that just be careful, I'm using this form which is the midterm. So that actually is f equals, so first these actually this set. So the x is 0, 0 here, it should be x prime. So and the yz, the y is 0, 0 should be y prime, and the z is 0, 1, it's actually gone, plus the next one, which is this and this. So again, the x is actually 0 in both of them, should be x prime. So and the z here is 0. So just wait a minute. So I'm writing for these two, 0 and 2. So the x is 0, x prime. So I'm here, y is here is 0, here is 1, it's gone. And the z here is 0, here is 0, should be z prime, okay? So you got this, you got actually x prime, y prime plus x prime, z prime, okay? So, but still this is just a function. You need to able to make a real circuit that able to do that. So then you implement these terms with the gates that you already know, okay? I'm implementing these actually function that I have. So if you do that, so I need how many inputs I have? I have actually I need 3 inputs, okay? So I need x. So I need definitely x prime. I actually need y and y prime. I need z and z prime. So I use actually this form, which is make our work more simple. So see, I just consider one column like this for each of them. So then this is actually the not. So this is actually is x prime. So the same thing, this is y. So this is actually take not, I make actually y prime here. So this is z. You directly could make this, but this form is probably more actually organized way to do that, especially whenever the function actually is more complicated and you have too many terms there, okay? So we actually have x, y. So now see how I could make this. You tell me how many ands do we need? How many ands do we need? The AND gate. How many ands? Yeah, 2. 1 for making this, 1 for making this, okay? So I put actually maybe use the other colors. It's actually should be more clear what you are doing here, okay? So see the first and, this is actually the first and. Put the first and here and the next and here. So the good things about this type, if you draw in this way, so you just, this actually has 2 inputs, right? One should be x prime, the next should be the y prime, but because we don't want to make our drawing very busy and we try to keep that very organized, you usually put just 1. So and you just put the circle on the input. So 1 input should be x prime. So I put here 1 circle here, which is x prime, and the next one should be y prime. Okay, so it means this and has 2 input. One is x prime and another one is y prime, right? So it's make that more organized. But you could directly have 2 input, okay? But again, if you use these format, especially whenever you have too many actually gates, it should keep your drawing more organized. Okay, so the next one should be x prime, z prime. So you have one here, which is x prime. So the next one is z prime, which is this. Okay. So then what do you need? Then we need one OR, right? You have one OR here. So you just put one OR here. So which is you put these two together, and this should be your output. So if we change the color, we could say here is on my F, right? And what I have here is I have here prime y prime, right? What I have here, I made x prime and z prime, okay? So that's it. If we had the lab, so you could actually implement this circuit that you see here on the breadboard with just using actually 2 and 1 OR. You connect the LED here on the F, and you need just 3 switch, one for X, one for Y, and one for Z, and also you need 3 NOT gates, so 3 switch for X and Y and Z, and 1 LED for F. So whenever, and you could actually definitely make all of these 8 cases with that switch, right? So whenever the input is smaller than 3, you actually see your LED is on. So if that's actually is 3 or greater than 3, the LED is off. Even if you are interested, you could simulate your circuit in the multisim and see it's actually working that way. So this is what you want to do, right? So this is, they actually want to design this kind of the circuit that able to get 3 inputs and tell us that is smaller than 3 or greater than 3, okay? So any question? So which is actually very cool. So right now, if you need any circuits, this is actually the knowledge that you need to get. Okay, whatever we learned so far is just for this concept, right? We want to able to design any combination circuit that we need. Okay, as engineering, you should be able to do that, and based on the knowledge that you got, we are actually able to design that circuit in the simplest form that possible, because we use actually the K-map, which is end up with the simplest form that we have. So you could actually make too many actually cool circuits, right? You could actually make a circuit, add to a number. You could make the adder. You could actually make subtractor. You could actually make any circuit that's able to square the input, okay? So we have one question: is there a shortcut to get the product of the mock stem, or do you have to repeat the process? So is there a shortcut to get the product of the mock stem? You mean the simplest form to the form of product of the mock stem? Okay, yeah. If you don't like this form that you see here, right? If you don't like this, which is somehow is the sum of the product. If you want to get the simplest form as a product of the sum, you need to actually start your K-map shouldn't be used these midterm. You need to use actually this form that you see here, okay? So that means here you should put the 0, here you should put the 0, here you should put 0, here 0, here 0, and get rid of these one, okay? So then actually find the new sets, which is again, the number of the sets should be minimum, their member should be maximum. Then if you write the corresponding sentence for each of these terms, you actually end up with the simplest form, but this simplest form should be in the form of the actually product of the sum, okay? So if you do that, so it shouldn't be need more than these gates that you use for this form. It should be almost simple. If you just consider from the actually the simplest form. So the both of them actually should use the same number of the gates. You could do that, okay? So you could do that by using this form, not this form. But definitely whatever you got, definitely the number of the gates should be same with this form that you have. And definitely that circuits will do exactly the same thing that you want to do, which is just detect the number if the number is smaller than 3 or greater than 3. So I don't know, this is the answer for your question, or you got your answers? Okay, yeah. So again, if you do that, again, maybe you end up with the different circuit, but the number of the gates you use should be same, which means that again is the simplest form, right? But maybe you use the different actually configuration, not whatever you see here. So definitely for that form here, you should get one AND, because you end up with the product of the sum, right? I just guess. So here should be changed to the and these two should be changed to the OR, because it's actually end up with the product of the sum. For sum, you need actually OR. Probably you will have two OR here, and you need one and here. Okay, that's my guess, but you could do that. Definitely you end up with the same.